Hi there, welcome back to the channel, and in today's video I will be introducing to you the transient response of an inductor. What I mean by transient response now is when the inductor charges and when the inductor discharges a current. And just to start off this video, I will be elaborating on what I mean by the transient response. Okay, so to help me explain this, let's consider this plot. On the x-axis we have time. On the y-axis we have a function, in this example, x of t, and this is what the plot would look like. Let's divide it into two, essentially dissect this plot. On the right hand side we have what's known as steady state condition. In other words, so the time has now increased to such a value so that y value, x of t, no longer changes and remains constant, hence steady state. And on the left hand side we have what's known as transient response. In the context of electrical engineering, the definition for transient response is the response of a system to a change from an equilibrium or a steady state. And in this video we're looking at the transient response of an inductor. So in other words, in the case of an inductor, how will it perform when we apply a voltage to it? Because that will be the change from equilibrium. So here we have an inductor on the right, and it can charge. The plot for the current against the time would look like this when it charges. Just like that. And when it discharges, the plot would look like this. But one common factor of these two plots is that they have what I've just shown you. They have both steady state and they have both transient response. On the right hand side and the left hand side, here we have steady state. On the left hand side we have transient response. So now that we're moving on to the topic of inductors, I will be elaborating on the equations you need to use to define these plots. Let's now consider an RL circuit. Here we have the voltage source, Vs, point A, point B, a switch that can connect to point A or point B at any given time, and here we have a resistor, R, and an inductor, L, hence RL circuit. And the current across that inductor, IL of T, is considered to be the output of this circuit. So let's now consider when the switch connects to point A. At point A, the inductor is now charging. Now, something I want to make clear is I won't be really showing you in this video how to derive the formula for the charging and discharging of inductors. I'll just be showing you the equations you need to use rather than how to derive it, because I think knowing how to use it is more important than deriving it, since many equations these days are available online at your disposal. So, let's consider the current. The current across the inductor as it charges is modeled by this equation. IL of t equals voltage source divided by resistance, that's Ohm's law, multiplied by the bracket of 1 minus E to the power of minus R divided by L multiplied by T and close the bracket. Now, for the case of voltage across the inductor, it's slightly differing, and it's modeled by this equation. Voltage source multiplied by, this time, just the exponential E to the power of minus R over L times T. Now, let's consider when the switch connects to point B. At point B, the inductor is now discharging. The current formula for when the inductor discharges is modeled here. It's Vs, voltage source, divided by resistance once again to get the current. This time just multiplied by the exponential, minus R over L times T, just like that. And for the voltage, it's just a case of VL of T, this time equals minus Vs, that's important, multiplied by E to the minus R over L times T. Those are the four equations you really need to be aware of when modeling the transient response of an inductor. And there's one more equation that you should know, is the time constant of an inductor. On the left here, tau equals L over R. That's the time constant of an inductor. And a general trend of when the inductor charges or discharges is that it takes typically 5 time constants to reach a full charge or a full discharge. So here we have IL of t on the y-axis and time on the x-axis. And this is what the plot would look like if we consider the inductor when it charges current and discharges current. It would look like this. At this point here, it's about 5 tau. And this is the time of discharging. And here is 5 tau again. So you don't just add on 5 tau each time, because you could discharge at any random time, not 5 tau. So that's something you need to be aware of as well when plotting this results. So now I think this covers the general basics of transient response. So to test your knowledge, there are a few problems in this video I want you to solve for an RL circuit. For this problem, we have an RL circuit, and I want you to complete parts A, B, C, and D to solve the overall problem for this RL circuit. So just a little walkthrough here. At part A, at time equals 0 seconds, the switch connects to point A of the circuit, and you are to calculate the value of the time constant. Part B is how long will it take for the inductor to reach a full charge of current. Part C, when the time is equal to 1.5 milliseconds, the switch connects to point B of the circuit. This changes the overall time constant for the circuit, because this affects the overall resistance, and you have to calculate the new time constant. Part D is to plot and label the current across the inductor as a function of time for the duration of 6.5 milliseconds. Take your time if you need to, and pause the video to work on the solution. Okay, let's start with A. Question A. Tau, time constant, is equal to the inductance divided by the resistance. The overall resistance when it's connected to switch part A, point A I mean, is 400 ohms. So here we have really is 100 millihenries, in other words times 10 to the minus 3, 100 times 10 to the minus 3, divided by 400, that's 300 plus 100. This is equal to 0.25 milliseconds. Now for part B, how long will it take for the full charge of the inductor current, or rather current across the inductor? Well, if you recall correctly from the theory I previously discussed, it takes 5 tau, 5 time constants to reach a full charge, and likewise 5 time constants to fully discharge. Question C. At t equals 1.5 milliseconds, the switch connects to B. What is the value of the new time constant? So this time we have only 100 ohms as the resistance. So here we have 100 times 10 to the minus 3 divided by 100. That gives us an answer of 1 millisecond. Now for the final question, D, is to plot and label the current across the inductor as a function of time for the duration of 6.5 milliseconds. So let's plot this. Okay. So here we have the initial rise of the current as it charges. Here we have 1.25 millisecond. And here we have 1.5 millisecond. So this is when the full charge, and this is when the 1.5 milliseconds is when it starts to discharge, because it connects to point B. And then we have this longer discharge because of the new time constant. And here we have 6.5 milliseconds. And that's the solution for each part of the questions. So that's all I have for today on the transient response of an inductor. I hope you enjoyed and learned something new about how that works. And I'll be looking forward to seeing you in next week's video.